Hello and welcome back to Algebraic Vectors lesson. This time we're going to take a look at identifying whether vectors can be parallel, perpendicular, and neither. And before we take a look at these examples, I invite you to take a look at some very simple investigations that will help us a lot in solving or answering such questions or identifying parallel or perpendicular vectors. So two vectors we're going to say are collinear if they are lying on the same line. So for example, if this is a straight line and we have two vectors in here, so this vector here and this vector right here. So these two vectors are collinear, vectors A and B. Let's give them a name, okay? Now, also, two vectors can be parallel. So for example, you have this vector A here and this vector B. Remember that we can shift the vectors on the plane in any way we wish, as long as we do not change the direction. So as you can see here, these two vectors, A and B, are parallel to each other. Now, when it comes to direction is not involved in the fact that the vectors are collinear or parallel. For example, vectors A and B, in this case, even though heading in opposite directions, they're still considered to be parallel to each other. And similar to this, these two vectors, A and B, are considered to be collinear even if the direction of vector B will be pointing into the opposite of vector A. So in order for us to understand how collinear or parallel vectors are related to each other, I drew a vector on the Cartesian plane. The coordinates of this vector are 7, 3. So this is a position vector. So let's build together a vector that is collinear to vector 7, 3. So this time I'm going to go in the opposite direction. I can go either opposite or in the same direction as the given vector. So 1, 2, 3, 4, 5, 6, 7. So this will be a 7. And I'm going to go actually this time, I'm going to go as far as here, for example. So I'm going to call this the vector B, and here is vector A. And we'll say that vectors A and B are collinear, okay? Because they lie on the same line. The directions, as you can see, are opposite. And we will identify the coordinates of vector B here. So vector B will have coordinates negative 3.5 for x and negative 1.5 for y. Now, if you look at the coordinates of vector B, negative 3.5 and negative 1.5, and try to relate them to each other, to coordinates of vector A. So we'll say that vector A, or let's put it this way better, vector B would be equal to, notice how negative 3.5 is 7 divided by negative 2, and negative 1.5 is 3 divided by negative 2. So it seems that to obtain the coordinates of vector B, we could have simply divided the x of A by negative 2 and the y of A also by negative 2. So in other words, we're going to say that vector B is half in magnitude as vector A, and it's heading in the opposite direction. So that means that negative 1 over 2 and then 7, 3. So we're going to say that vectors A and B are collinear because they can be expressed as scalar multiples of each other. So this would apply for two vectors that are parallel to each other. So in general, we'll say that if two vectors are parallel or collinear, it means that we can express them as scalar multiples of each other. So if we prove that some vector A equals k times some vector B, it means that the two vectors are collinear. So if we can find that multiplier k, that will make this vector here equal to the vector on the left. Now, in a similar way, we'll discuss two vectors that are perpendicular. So this time, we have that same vector with coordinates x equals 7 and y equals 3. Let me bring this a little bit closer. All right. And we are going to build a vector perpendicular to the given one. So what I'm going to do here is go 90 degrees from the origin. So if I want to go 90 degrees from the origin, it means that this is where I have to build the vector. So these will be two perpendicular vectors. So this is vector A with coordinates 7 and 3. And this is vector B. And vector B has the coordinates, as you can see in here, x negative 3 and y equals positive 7. So if you look at these two coordinates, or the coordinates of these two vectors that are obviously perpendicular because we built them to be perpendicular, then notice that the coordinates have switched. So from 7, 3 become 3, 7. And one of the coordinates has switched the sign, so x has become negative. Now remember that a perpendicular vector to A can be drawn in this direction, but it can also be drawn in this direction. So if we went this way around, then this would be another case of a perpendicular vector. I'm going to call this actually the vector C. Let's give it a name, and we'll make it blue, why not? All right, and this is vector C. You can see that it makes the angle 90, and the coordinates of vector C are x equals 3 and y equals negative 7. So if you compare it with coordinates of A, you see that 7 and 3 has switched to 3, 7, and only y is negative. So for two vectors to be perpendicular to each other, we need to have a switch in the sign. So one of the coordinates has to switch to negative. It can be either x or y. And the other coordinates will either switch, but if you imagine, you can make this shorter, it's still perpendicular. So the coordinates must be scalar multiples of each other and must have a switch in the coordinates. So the switch will happen the other way around. This is something that we are going to discuss in more details when we find the equations of lines and planes, which will be in the next unit. But for now, our main focus will be to identify whether vectors are parallel. So I'm going to look at our first example here for negative 9 and negative 9, 4. So this would have been the case of two perpendicular vectors, but I can tell right away from what I remember from my investigation that here we have the switch in the sign of the coordinates for both of them. So I'm not sure what is happening, but I'm about to find out. So I would say that first I need to check if they are parallel or collinear. So here are my explanations. I'm going to say collinear. All right. Therefore, we must be able to express vector u as the multiple of vector v, which means 4, negative 9 must equal some multiplier k times negative 9, 4. So now we have to use the coordinates x and y in order to see if we get the same multiplier k. So we're going to say negative 4 and positive 4, negative 9. We don't need to write the positive actually. So 4, negative 9 must equal negative 9k and positive 4k. Okay, so we're multiplying by the scalar. And now we have to find out what k value will guarantee that 4 will equal negative 9k. So we'll say 4 must equal negative 9k, which means that the k value must be 4 over negative 9. Now, we expect to have the same k value that we can derive from equating the y coordinates. So let's hope that happens. Negative 9 equals 4k. So k in this case will be negative 9 over 4. And negative 4 over 9 over 4 and 4 over negative 9 are two different numbers, different values. This is negative 0 point close to 5, and this is going to be a number less than negative 1. So it's going to be negative 2 point something actually. So negative 2.25. So because we got two different k values, then we'll say that these two vectors are not parallel or not collinear, okay? So let's take a look at what they appear like on the Cartesian plane, and I'm just going to eyeball it actually because we're not scaling everything. But if we have the vector 4, negative 9 means that, let's say, for example, this is 4, and negative 9 must be somewhere just below this. So this would be the first vector for negative 9. The second vector, negative 9, 4, would be, if this is 4, this would be 4 and then a little bit more. So this would be the second vector. So you can tell that the two vectors are not collinear just by doing the graph of it. In the same way, you can practice the next question, but in this case, the vectors are not given in component form, but they're given in standard form. Okay, so you can try this on your own, and now we're going to take a look at the next example, example number 12. We're given 3 points, and we're asked to determine whether they are collinear. Now remember that if you have 3 points, and I'm just going to draw some, random sketches in here. So if 3 points are collinear, for example, we have the points A, B, and C, all lying along the same line, not necessarily equidistant to each other. Okay, so here is some point C. And we're going to say that we should be able to express AB as a scalar multiple of BC, right? So or we can express it as, or we can have AB equals the scalar multiple of AC, or AC equals the scalar multiple of AB. So any vectors that are formed on this line can be compared to each other by using a scalar multiple, right? So if that is true, then we would say that, oh yes, they are collinear. But if they're not collinear, so if they are not lying on the same straight line, it means that it will be impossible for us to find the value of k that can make that happen. So let's get started then with our question. So how do we determine that they're collinear? So we're going to start from this statement here. And as you can see, we need to find the vectors to compare because what we're given is simply the coordinates of a point. And what I'm going to do is compare vectors AB with BC. Vector AB will have the coordinates 3, minus 1, and 3, minus negative 1. Remember how we find the coordinates, right? So you start from x of b, take away x of a, which means 3 minus 1. And then y coordinate is y of b, subtract y of a. So AB will have the coordinates x equals 2, y equals 4. Now let's do BC. So for BC, again, we're looking at x of c minus x of b. So that would be negative 4 minus 3. And then y of c minus y of b. Y of b here. So it's negative 11 minus 3. So that would equal negative 7, comma, negative 14. So we're going to say that if we're able to find a scalar or a number that can relate AB with AC by the equation AB equals KBC, then the two vectors will be collinear. So let's take a look. AB was 2, 4, and BC was negative 7, negative 14. Okay, so what that means is 2, 4, we're expecting it to be negative 7k and negative 14k. So let's solve for k. Again, we're going to do the same thing. We are going to equate the x coordinates to see by what scalar have they been increased or decreased, right, or multiplied. So we'll say 2 equals negative 7k means that k must have been negative 2 over 7. Similar to this, we are hoping to get the same k value here. Remember, the y coordinate k must equal negative 14k, 4. I don't know how this happened. So the best way to admit a mistake is by making fun of yourself. Here we go. So here we go, 4 equals negative 14k. So that would give 4 over negative 14 equals k, and that equals negative 2 over 7. So we're going to say, voila, we got the same k value, which means that the two vectors are connected to each other by a multiplier k, and that means that the two vectors, the 3 points, are lying on the same line. So the answer is yes, A, B, C are collinear. Collinear points. All right, so I think this is going to be our last example. Yes, that is true. And we have 3 points, and we are told that the 3 points given are vertices of a parallelogram ABCD, and we need to find the third coordinate of this parallelogram. So first I'm going to draw a parallelogram, and I want to actually point out one very important fact, that whenever we draw a parallelogram, we have to, it is very important how we label the vertices. So it has to go in order. So this looks like a parallelogram, right? So that's A, B, C, and D. So we want to go A, B, C, and D. You don't go A, B, and then C and D here. That would be wrong. So we're going to say A is negative 1, 4, and 0. B is 2, 1, and 1. C is 2, negative 2, and 1. D is X, Y, and Z. We don't know what D equals. So we want to find the coordinates of D, but we know that this is a parallelogram. Now, in order to find coordinates of D, we're going to have to think of what properties of parallelograms can we use in order to find the coordinates of point D, because this is a parallelogram. Then point D cannot be just anywhere. It has to follow, or it has to complete all the properties of the parallelogram. Now remember that a parallelogram has two sides that are parallel, and these two sides that are parallel to each other. So one of the ways to prove that this is a parallelogram is by finding vector DC and vector AB, and proving that these two are parallel to each other. And if they are parallel to each other, then that means that the other two sides have to be parallel as well. Another way of proving that this is a parallelogram is by finding the magnitude of each side and then comparing them, the respective sides. I am going to try to prove this by using the parallel sides. So I'm going to say that vector DC must be x at D, which is 2 minus x minus x at C minus x of D, y of C minus y of D, and then y of z of C minus z of D. So we have negative 2 minus y, and then 1 minus z. So that means that vector DC, this is simplified actually. I thought that we need to simplify something. On the other hand, we have vector AB. Now, vector AB will have the coordinates x, 2 minus negative 1, y, 1 minus 4, and then z, 1 minus 0. Now, vector AB will be 2 minus negative 1, 3, 1 minus 4, negative 3, and 1 minus 0 is 1. Now, if we had these two vectors, right, on the Cartesian plane, and we place them on the Cartesian plane as position vectors, what do you think would happen? So, would their respective position vectors will have exact same coordinates? Since these two are equal vectors, they're parallel, right? Parallel, and they have the same length, because that's a parallelogram, then we're going to say that since ABCD is a parallelogram, then the corresponding position vectors must be the same. So, or equal. So we'll say that vector DC equals vector AB. And we're following the directions as well, right? That's important. So, which means that